Hello everybody, welcome into another lesson. So today we're going to talk about proportional lengths with triangles. So up first here we have the Triangle Proportionality Theorem. This states that if a line parallel to one side of a triangle intersects the other two sides, then it divides those sides proportionately. So to illustrate that point, I have triangle ABC where you have DE that is parallel to side BC and it intersects sides AB and AC. Based on this theorem, we can say that the length of BD is in the ratio to the length of DA. That's going to be equal to the length of CE in ratio to EA. That's exactly what that would say. And I have some exercises to practice this theorem. So the Triangle Proportionality Theorem is a very nice theorem to know. Though we're not really doing proofs anymore, still it's very good to know it. Okay, so I'm going to draw a few triangles here. See, this side is parallel to this side. Then what do they give us? This has a length of 4 up here. This has a length of 5 down here. This has a length of 6. This has a length of x. Okay. So we're going to put the Triangle Proportionality Theorem into practice. So how this is going to work is we're going to take the ratio of 5 to 4 on this side. So we'll have 5 to 4 will be set equal to x to 6. And then you just simply got to solve a proportion, which isn't too bad. Well, that would give you 4x equals 30, which would then just give you 30 divided by 4, that's 7.5. So the value of x that you should get would be 7.5 when you solve the proportion. And yes, it is normal to have decimal lengths. Really, this theorem is actually pretty dang easy to understand. I know when we wrote out the theorem it looked kind of long and wordy, but it's a very simple one to understand. Alright, now they're flipping it around on us here. Let's see what they give us. Alright, those two lines are parallel. This has a length of 12, the small segment, but the whole thing here has a length of 33. The whole side here has a length of 33. This segment here is a line of 20. This part here has a length of x. So, okay. So we have our triangle again with a line in the middle of the triangle parallel to the base. Well, according to the Triangle Proportionality Theorem, all these parts of the sides are proportional to each other. So here's the thing though. We have x and 20 on this side. They're divided into different numbers. We know the length of this whole side here is 33. We only have 12 for the small segment. What I'm going to do then, we probably want to find the length of this, don't we? You would just take 33 minus 12, which would give you a length of 21. If you took 33 minus 12, you would actually get a length of 21 for this segment. That's all you want to do, is you probably want to find the missing length first before you set up proportions. Now, let's go ahead and set up our proportions then. That's going to be 21 to 12, so take 21 to 12. set that equal to x over 20. Well, one thing you probably want to do here to help yourself out, don't 21 and 12 simplify? Don't they both have a common factor of 3 that we can divide by to simplify the ratio? I would do that first. If you did that, you would get 7 to 4 equals x over 20. I think 7 to 4 is much easier to work with than 21 to 12. Now we'll just take the cross products. You would end up getting 4x is equal to 140. Which, if you took that, you would end up getting x is equal to 35. So the length of x would in fact be 35. Couple more examples with this. Alright, there's another triangle. Wow, let's bring it all the way up here. Whoops. Don't want to use that one just yet. There we go. So we have a tilted triangle with this line here parallel to the base. Let's see what we get for lengths. This little segment here on this side has a length of 10. Now the whole length here of this side is x. The length of this entire side is x. The length here is 15. The length here is 24. Well, what we're going to do now, again, you probably want to find the missing length here, don't you? So you can solve for, so you can set up your triangle proportionality theorem. If the whole length is x, this length is 10, that means the length of this segment would simply have to be x minus 10, wouldn't it? You would end up getting x minus 10 for this length. Now you may set up your proportions. So we can say x minus 10 is in ratio to 10, which would equal 24 to 15. Well, before we go any further, can't 24 over 15 simplify further? They both have a common factor of 3, which will end up giving you x minus 10 over 10 equal to 8 over 5. I think 8 over 5 is much easier to work with than 24 over 15. So now you do your cross product, you end up having 5 times the quantity of x minus 10 equal to 8 times 10, which is 80. Well, you can divide both sides by 5. If you do that, you'll get x minus 10 equals 16, which would then simply have to give you that x would equal 26. So the value for x is that you would end up getting 26. I have one more with this theorem. One more exercise with this theorem. All right. See, this is A. See, we have Rn here. TP, okay. And of course, Rn runs parallel to TP. Alright, so we're also given a table here. Well, no, I'm not going to put it in table form, but instead I'll explain what we're going to do. So the length of AR is going to be 6. The length of RT is 4. What else are we given? AN has a length of 9. We don't know NP or AP or RN, but TP has a length of 15. Okay, so what we need to do now, we need to find the length of AT, the length of NP, the length of AP, and the length of RN. We have to find the lengths of those that are missing. Well, if we use the segment addition postulate, isn't it true that the length of AT equals the length of AR plus RT, which would then simply give you, of course, AR is 6 plus RT, which equals 4. Therefore, the length of AT would have to equal 10. So we found the length of AT. That happens to be 10. Now, we don't know the length of NP. That's okay. What we can do is use the Triangle Proportionality Theorem. So that's going to be TR, which would be the length of that. That'd be 4 to 6 on this side, would be equal to PN to the length of AN, which would be 9. Well, 4 to 6 we know reduces to 2 to 3, right? So then you would have 2 to 3 equals PN over 9. Which then is going to give you, if you do the cross product, you would have 3PN would equal 18, which means PN would have a length of 6. So we found the length of PN, and then next thing to do is find the whole length of AP. Well, use your segment addition postulate. The length of AP is equal to the length of AN plus PN, which we know AN was equal to 9 plus the length of PN we found to be 6. So the length of AP equals 15. Okay, so far we have found the whole length of AT, we found the length of PN, we found the length of AP. All that's left is to find the length of RN. Well, this is where, if you're going, we've done the Triangle Proportionality Theorem so far, but for RN that's going to change. It's going to be like the exercises we did before today's lesson, where RN's the base of the smaller triangle to the whole triangle that it's inside of. So, your scale factor is going to be 2 to 3, right? Your scale factor was 2 to 3. We've determined that already. Now, if your scale factor is 2 to 3, that means we consider the small side first, the RN, to the base of the whole thing, which is 15. And then you just do your cross product, you would end up getting 3RN equals 30, which could only then give you that RN would have a length of 10. So you'll get some puzzle problems like this where you'll have to solve for all the missing lengths. So RN ultimately would have a length of 10. So, of course, to find AT, which was one of the missing lengths, you just add the lengths of AR and RT together. 6 plus 4 gave you 10. To find the length of NP or PN, you set up your Triangle Proportionality Theorem, which ended up giving you that PN equals 6. And then to get AP, you just add the lengths of AN plus PN. And you got 9 plus 6, so AP equals 15. And then the length of RN is proportional to the whole triangle. When you set up that proportion, you get a length of RN being 10. Alright. So next I have a corollary and then a whole nother theorem. But first there's a corollary to this theorem that has its own exercises. Alright, let's discuss what that corollary is going to say. So this is the corollary to the Triangle Proportionality Theorem. It states if three parallel lines intersect two transversals, then they divide the transversals proportionally. All right, I'm going to illustrate this here. Alright, let's denote that these three lines are parallel to each other. Okay, now, what we have here is a corollary that states if three parallel lines intersect two transversals, then they divide the transversals proportionally. So, you see three parallel lines here, but you have two transversals, RT and XZ, that go through those parallel lines. Earlier in the course, we had talked about a theorem that stated if three lines are parallel to each other and equidistant to each other, then and they're intersected by transversals, then it divides the transversal into congruent segments. It's similar, only in this case the parallel lines are not equidistant apart. So that's why it's proportionally. So this is a different thing entirely then, because these lines are not equidistant apart. So in other words, what you're looking at here is that you're going to have TS would be in proportion to SR, which would be equal to ZY in proportion to YX. So if we look at this diagram here, TS would be in ratio to SR, which would be equal to the ratio of ZY to YX. That's what this corollary states. And I have three exercises here for this corollary. Alright, so what are we given here? Just a hint, this is going to be another solve for x. This will be another solve for x1. Of course, these three lines are parallel to each other, which that's going to help us. This one here has a length of 22. This has a length of 11. This has a length of 29. This has a length of x. Okay. So we're going to use the corollary that we just learned about the parallel lines and solve for x. So since these lines are parallel, cut by two transversals, it divides the transversals proportionally. So set up your proportion, which would be 11 to 22. That's going to be equal to x over 29. Well, 11 to 22 simplifies to 1 to 2, right? This would turn into 1 to 2 equals x over 29. Which now when you do the cross product, you would get 2x equals 29, which would then just give you that x equals 14.5. 14.5 is half of 29, so x has a length of 14.5. So it's almost like the triangle proportionality theorem. In fact, that's why it was a corollary to that theorem, only it deals with segments. It deals with transversal lines and parallel lines and the segments they create. So it's pretty similar to the triangle proportionality theorem. I got two more exercises with this corollary, then we're going to go on to our last theorem of the day. And then we'll have some exercises with that too. Okay. What is the next one? They flip it on us. Then it goes all the way over here. And then we have close by it another line. Okay. Let's see. We are given again that these three lines, these three vertical lines are parallel to each other. This segment has a length of 18, this one a length of 9. This one is 24 minus x. This one is just x. Okay. So once again, we got to solve for the value of x. Well, let's take 9 to 18. 9 to 18 is going to equal x to 24 minus x. Before we go any further, 9 to 18 simplifies into 1 to 2, right? So now you'll have 1 to 2 is equal to x over 24 minus x. Which now will take the cross product. You would end up getting 2x equals 24 minus x, which would become 3x equals 24, which would then just give you that x equals 8. So the value for x in this case would just be 8. So this corollary is also pretty simple to understand. One more exercise with the corollary. All right, slight grade here. Bigger grade there. Okay, so These three lines are, of course, parallel to each other, cut by transversals. So they give us a length of 4x here, 3x here. What do they give us on the next set? 5x and then 15. Okay, so we have to solve for x. So go ahead, set up your proportion. We could take 3x to 4x. So 3x to 4x would be equal to 15 to 5x. Whoops, I almost wrote that wrong. It would be 15 to 5x. Okay. In this particular case, both sides will simplify, won't they? On the left side, you can cancel out an x between the numerator and denominator, which would just give you 3 to 4, would be equal to the right side. Well, both numerator and denominator on the right side can divide by 5. That would give you 3 over x. I think this is much easier to work with. So now, if we do the cross product, you would get 3x equals 12, which would then just give you that x equals 4. 16 to 12, 20 to 15. Yep, all right, and it would check out. So the value you should get for x would be 4, and you would end up getting the same ratio of 3 to 4 for each of these lengths. So the value of x you get in this case is 4. Now, the theorem we're about to do is not super hard, but it's harder than what we've talked about today. This one is going to be called the Triangle Angle Bisector Theorem. It's a big one. All right, let's see what that states. All right, and of course I gotta draw a triangle. To illustrate what the heck I'm actually talking about. Let's see what we got here. All right, so next here is the Triangle Angle Bisector Theorem. It states that if a ray bisects an angle of a triangle, then it divides the opposite side into segments proportional to the other two sides. Okay, so what does that mean? Clearly we see ray DG bisects angle FDE of this triangle, right? You got the congruency markers here, meaning it bisects that angle. Well, when you have that, it divides the opposite side, which would be FG, or it would be FE. It divides it into FG over GE, right? So FG is in ratio to GE. Now, with the ratio of the other two sides, it's going to go in the order you started in. If you started at the left, you would put FD as the numerator of your second ratio, and then the right one, the DE, as the denominator of your second ratio. If you started at the right, then it would be GE over FG to DE over FD. But I find it easier to start at the left and work my way right. So whenever you set up your proportion, it's going to be, of course, the opposite side. It'd be FG over GE to FD over DE. You got to make sure you set up your proportion correctly. That's where a lot of people go wrong solving these types of problems. This is what trips people up with the Triangle Angle Bisector Theorem. You got to make sure you set up your proportion correctly. A lot of the time, people have no trouble setting up the opposite side, but when it comes time to do the other two sides, they set it up in reverse, and that's where they make the mistake. So, if you start at the left, stay left. If you start at the right, stay right. That's a good way to remember it. And I got some exercises for this too, that I will illustrate this theorem with. The Triangle Angle Bisector Theorem. Alright. So we have a triangle here. Alright. Let me place the congruency markers on this angle. This has a length of 14. This has a length of 21. This has a length of 8. This has a length of x. Okay. So we're going to perform the Triangle Angle Bisector Theorem. As you can see, this angle of the triangle here is bisected, right? With the congruency markers. So when you go to set up your proportion, we're going to start at the left. That's going to be 8 to x from the opposite side. We'll have 8 to x would be equal to, since we started at the left, that would be equal to 14 over 21. But 14 to 21 reduces, right? That would end up giving us 8 over x is equal to 2 over 3, which would make this much easier to work with. So then now you set up your proportion, you solve for the cross products, you would get 2x is equal to 24, which would then give you a length that x is equal to 12. So x itself equals 12, and that would still be in the ratio 2 to 3, so that's perfect. So x has a length of 12. And I got more exercises for this. Alright, so here is the bisected angle. Let's see what they give us here. This is 42 minus x on the left. This is just x here on the right. Let's see what else they give us. Length of 36, length of 27. Okay. So another exercise with the Triangle Angle Bisector Theorem. So you see your bisected angle with the congruency markers. So I'm going to start at the left again. That's going to be 42 minus x to x. So always start on your opposite side first. Start at the left to the right. It'll be the ratio of the left to the right. That's going to be equal then to the left side, which would be 36 to the right side, 27. Well, we know 36 to 27 simplifies, right? This would give you 42 minus x to x. Since both of these divide by 9, that would just give you 4 to 3. 4 to 3 is so much easier to work with than 36 to 27. Now you do your cross products, you'll end up getting 4x is equal to 3 times 42 minus x, which would then give you 4x is equal to, what's 3 times 42? So 2 is 84, 124, 126. That'd be equal to 126 minus 3x. Simplify this further, you get 7x is equal to 126. And offhand, I don't know what 126 divided by 7 is, so I'm going to find out. It's 18. Okay. So x would be equal to 18. So you get the length for x being 18. If you want to check your work, always stick the value of x that you got in, that 18 in, for where x is, and see if the ratios measure up, if the scale factor still measures up. If it does, you've done it right. If it doesn't, then you probably reversed your ratios in the proportion and probably set it up wrong. Okay. A little bit different here. It looks similar, but may not be the most accurate drawing, but that's okay. Whoops. No, I want you to be able to see the ray that bisects the angle. I better make that black instead of red. There we go, that's more like it. This again will be the bisected angle. Let's see what we get this time. This has a length of 18, this has a length of x. Ah, yes. The whole length of this segment is 40. The length of just this side is 25, right? Well, okay. Again, the sides are divided proportionally. If this side has a length of 25, if just this part does, the length of this whole side's 40, I think it's obvious then that the length of this is 15. I know it's not the most drawn to scale, but you'll get the picture. Because 40 minus 25 is 15, so the length of this would be 15. Now we can set up our Triangle Proportionality Theorem. So that's going to be 15 to 25 would be equal to 18 over x. Well, 15 to 25 simplifies. That would become 3 to 5 equals 18 over x, which would then give you 3x equals 90, which would then have to mean that x equals 30. So the length you should get for x would be 30. Now I have 4 more exercises left with this theorem, but it's going to be a little bit different. the Triangle Angle Bisector Theorem is a very important one. Of course, this is obviously here, this is your bisected angle. In this case, we're given that AD has a length of 21. We're given that DC has a length of 14. Then, here's what's interesting. We're given that the whole length of AC is equal to 25. The whole length of that side AC is 25. What they want us to find is AB. We have to find AB. So how in the world are we going to do that? Okay. What we're trying to find, of course, is AB, right? According to the Triangle Angle Bisector Theorem, it divides the opposite side and the other sides proportionally. Well, we're trying to find AB, so the ratio is going to be AB. It would ultimately be to BC, but the whole length is 25 for AC, right? If we do 25 minus AB, we get BC, don't we? So that's actually going to be AB to 25 minus AB. So now we figured out the two sides, the two segments here. It's AB to 25 minus AB. That's going to be equal to 21 over 14, which 21 to 14 reduces. That'll end up giving you AB to 25 minus AB would be equal to 3 over 2. And 3 over 2 is much easier to work with than 21 over 14. So if we do our proportions, we do the cross product, you'll take 3 times 25 minus AB, set that equal to 2AB, which would then give you 75 minus 3AB would be equal to 2AB, which if we simplify this further, you would end up getting 5AB equals 75, which then means that the length of AB would be equal to 15. So this is one of those you had to actually consider the length of the whole side, consider what you're trying to solve, and then that BC is just 25 minus AB. That's how you would set up the ratios. You ultimately get that AB has a length of 15. Alright, 3 more exercises, then we're done for the day. The triangle's not going to change, but some lengths are, and what we're trying to find even will change. Alright, this time they give you that the whole length of AC has a length of 60. What else? CD has a length of 30. And AD has a length of 50. What we have to solve for is BC. We have to find the length of BC. So once again, how are we going to do that? Well, start with your opposite side, okay? Start at the left. We're ultimately trying to find BC. Well, isn't it true that the length of AB would just be the whole length of 60 minus BC? That would be the length of AB. So in this case, we're going to take 60 minus BC over BC itself. We're going to set that equal to, start on the left again, that'd be equal to 50 over 30, which would then 50 to 30 reduces to 5 to 3. So you could do this as 60 minus BC over BC would be equal to 5 to 3. Okay, now do your cross products. You would have 5BC is equal to 3 times the quantity of 60 minus BC, which would then give you that 5BC equals 180 minus 3BC, which would simplify into 8BC equals 180, which then BC is 180 divided by 8. I'm just going to do that one real quick on the calculator. That would give you 22.5. So BC ends up having a length of 22.5. That's what you would get in the end. BC has a length of 22.5. And yes, it is normal to get decimal answers. You can totally get that sometimes. Two more exercises, then we're done for the day. Let's see what we get here. Let's see, AB. Okay, AB has a length of 27. BC has a length of X. Okay, in this case, I can delete this whole line here. Then what else do we get here? CD has a length of, oh, this is going to be a fun one. We got fractions. 4/3 X. And then AD has a length of X. We ultimately got to find the length of AC. Let me state what our objective is here for this one. Find AC. Well, still, you're going to set up your proportions, okay? According to the Triangle Angle Bisector Theorem. Start with your base. Well, this would be in the ratio 27 to X would be equal to X over 4 to 3X. Well, right away we notice on the right side, X's will cancel out in the denominator, which would give us 27 to X would be equal to 1 all over 4/3. If you have a fraction in the denominator, you just invert it. This would really give you that 27 over X is equal to 3/4. Now this is going to give you that 3X is going to be equal to 108. Which then gives you that X is equal to 36. That's great, we found the length of X, but they really want the whole length of AC. Well, AC is equal to the length of AB plus BC, which would be equal to 27 plus X. We just got X being 36, that's equal to 27 plus 36. So the whole length of AC, if we do 27 plus 36, that would be what, 3363. So the whole length of AC would have a length of 63. Okay, so I started again with a triangle angle bisector. You set up your ratios. this would simplify into 27 to x is equal to 3 to 4. The value of x was 36, and then you just plug that in for where you have BC. You get 27 plus 36, which gives you that AC has a length of 63. I got one more exercise, then we're done for the day. Alright, let's see what we get for the last one here. This is different. AB is equal to 2x minus 12. BC has a length of x. CD has a length of x plus 5. And then AD has a length of 2x minus 4. We got to find the length of AC again. So this time we have all variables. We are going to find the length of AC. Well, let's still deal with our triangle angle bisector theorem. That's going to be equal to the proportion of these sides, which would be 2x minus 12 to x would be equal to your left side here. That'd be equal to 2x minus 4 all over x plus 5. There's really no way of simplifying. It's just not going to be pretty. We're going to have some quadratics. So the cross product here, that would be the product of the quantity of 2x minus 12 times the quantity of x plus 5. That'd be equal to the right side of x times 2x minus 4. Well, let's FOIL out the left-hand side. You would get 2x squared plus 10x minus 12x minus 60 equal to, let's distribute on the right side, that would be 2x squared minus 4x. Okay. Let's simplify the left side. That's going to give you 2x squared minus 2x minus 60 is equal to 2x squared minus 4x. Notice something. Between both sides, you can cancel out the x squared terms. This would leave you with negative 2x minus 60 is equal to negative 4x, which we can simplify this further. Add 4x to both sides, you get positive 2x. Add 60 to both sides, you get 2x equals 60, which would then just give you that x is equal to 30. X equals 30. That's great. We found the value of x, but we need to find the whole length of AC. So, of course, use the segment addition postulate that AC is equal to the length of AB plus BC, which originally AB was 2x minus 12, plus BC, which was x, which would actually give you 3x minus 12. So then if you substitute that 30 in for x, you would have 3 times 30 minus 12, which would give you 90 minus 12, which can only mean that AC has a length of 78. So, of course, if you set up your proportions according to the Triangle Angle Bisector Theorem, you solve, you get x has a length of 30. Then you stick in 30 for your x's here, you get that AC has a length of 78. So that's been it for today's lesson. Next lesson should be the last lesson of the proportional lengths of triangles. we're going to talk about concurrent lines, what those mean, and how they pertain to triangles and proportional lengths with those. So I hope everyone has a great day. Take care.